Hey guys, last lesson we were looking at ionic compounds and how they dissolve in water, and this lesson we'll be focusing on covalent molecular substances and how they dissolve in water. So just to remind you, covalent bonds are involved inside a molecule, not between molecules, and it's a sharing of electrons. So one electron is from the hydrogen, one electron is from the carbon here. And then they share the electrons to form a covalent bond. Covalent molecular substances include a list here, so hydrogen, oxygen, and all the diatomic forms. And usually they are insoluble in water: hexane, chloroform, kerosene, paraffin, and they don't have any polar bonds, and therefore they cannot interact with any of these. But some covalent molecular substances are soluble in water, and these include sugar, ethanol, urea, and they all depend on polarity. So in this case, a sugar molecule has some parts are polar, and therefore they can interact with certain water molecules. And therefore when they are put into water, they can interact and form some bonds, and therefore they can separate and then dissolve in the water. So water is a very polar molecule, which we've all looked at, and only polar molecules are soluble in water. Molecules that contain OH groups and NH groups can form hydrogen bonds with the water, and therefore they can dissolve. These molecules do not dissociate into ions, but remain as intact molecules, because remember, covalent bonds are really, really strong, and therefore they cannot be overcome and broken by water molecules just interacting with them. Covalent molecular compounds that form hydrogen bonds with water are soluble in water. Polar covalent molecular compounds that are soluble in water include urea, glucose, sucrose, ethanol, methanol. And this is because there's a formation of hydrogen bonds between the OH group and in methanol and the water molecules. So here's methanol, there, and there's an OH group here, OH group there. And because the OH group can interact with the water molecules, therefore they can attract each other and pull the water molecules apart, pull the methanol apart, and therefore disperse inside the water. Similarly, between water and other substances which are polar, hydrogen bonds can also be formed, and therefore they can be dissolved in water. So we'll look at size and solubility. Firstly, small alcohol molecules like methanol, there's only one carbon in there, and ethanol, a 2-carbon chain, are very soluble in water. Larger ones, such as 1-hexanol and 1-decanol, which are very, very long, are much less soluble compared to methanol. These larger molecules still contain the OH group, which can interact with water, so the hydrogen bonding between the OH group and water molecules, but because of the size, they're not the non-polar hydrocarbon part, so the carbon-to-carbon chain is much larger, and therefore that part can't interact with water molecules such as this one. So the water molecule really only interacts with the OH group, and if it's too long here, then there's too many dispersion forces that need to be overcome, and they become the dominant force and therefore can't be dissolved in water very well. So the solubility of alcohol depends on whether the tendency of the OH group is able to dissolve in water and is the predominant force involved. So if the OH group, the forces between the OH group and the water is greater than the tendency of the hydrocarbon chain part, so the dispersion forces, then it can dissolve in water. But if it's the other way around, the hydrocarbon part is stronger, then the molecule will be unable to dissolve in the water. So in smaller alcohol molecules, so shorter carbon-carbon chains, the OH group causes the alcohol to be soluble because that's the driving force, and then there's not as much dispersion forces to then be overcome. In larger alcohol molecules, the influence of the hydrocarbon part will limit the solubility because the dispersion forces are greater. So covalent molecular substances can be non-polar or slightly polar, but these ones can't form hydrogen bonds with water molecules. They only interact with water molecules via dipole-dipole or dispersion forces, which are very weak. Therefore, these substances are generally less soluble in water. So sometimes they can be partially soluble. That means they can dissolve a little bit, but not very much. So they're either described as being partially or slightly soluble in water. So partially soluble molecules can be elements such as nitrogen and oxygen, which are non-polar, and only dispersion forces are involved with the water. So nitrogen is a diatomic molecule with a triple carbon bond, so we can't break these covalent bonds. Water will then just only have dispersion forces because it's linear, not polar, and therefore only dispersion forces which are weak can be used to dissolve nitrogen into water. So these substances have very limited solubility and it's very, very low. So other ones are non-polar compounds such as butane and carbon tetrachloride, and these also are non-polar molecules. So when they're non-polar, that means there's only dispersion forces involved, and therefore they also will have low solubility. So polar molecule compounds include chloroform, ethyl acetate, and ether. These all can form dipole-dipole forces with water molecules. Dipole-dipole forces, remember, are slightly more strong than dispersion forces, but not as strong as hydrogen bonding. So these ones are, like I said, a bit more stronger, but not very, very, very strong. So when we look at solubilities, we can look at the solubilities of different gases and how they dissolve in water. Gases tend to be non-polar, and therefore we can compare the different solubility rates to look at how well they can dissolve in water. So we can see that hydrogen chloride here, remember, is an ionic compound and it's very soluble in water because it's 70 grams in 100 grams. But we can only really dissolve a very, very small amount, less than 1 gram of hydrogen gas in 100 grams of water. So as we move down the table, we can see that there's higher solubility, they're more soluble in water. So covalent molecular substances that react with water can be some polar molecules, which can chemically react with water to form new products. And this includes hydrogen chloride, hydrogen bromide, nitric acid, sulfuric acid. And in this case, because they so react with water, they can be very soluble in water. That means they're going to be dispersed into the water. So hydrogen chloride molecules undergo ionization, and this is when they're dissolved in water. So water is considered an ionizing agent, or ionizing solvent, because it causes ionization of the hydrogen chloride. So when we write this in a chemical equation, we have hydrogen chloride. Firstly, you can write it as a gas, G, and then water with L because it's a liquid form. And what it forms is this H3O, because H2O is neutral, there's no charge. We put an extra hydrogen, it becomes a positive. And this is in aqueous solution, so we write a little AQ here. That leaves us with the chloride atom, which is negatively charged, and that's also in an aqueous solution. So when we look at this for nitric acid, the same thing occurs. So we have nitric acid here in aqueous solution, and we mix it with more water in liquid form. We form more of this H3O plus ion, and then we are left here with the NO3 anion. And so the ionization is the formation of these different positive and negative charges when they are put into a water solution. So what is this H3O ion? It's hydronium ion. So it's water with an extra positive charge. So the formation of ions result in the solution of hydrogen chloride being able to conduct electricity, because remember, to conduct electricity we needed a positive and a negative ions inside the water to move about. And then we call these things electrolytes. Chlorine gas reacts with water, well, not very well, but it does, and it can be shown in the following equation where we have Cl2, which we've dissolved in water a little bit, so it becomes aqueous solution. And we put it with some water, some liquid, which is denoted by the L, and then we get an equilibrium, which is the two arrows. So some of it's going this way and some of it's going that way. So when we're going this way, the chlorine and the water react, forms HOCl in aqueous form, so it's in solution, with some chloride atoms, ions in aqueous solution, plus the hydronium ions in solution. But the other way can also occur. So we can have all these three reactants going together to form this again. So there's both ways. So solubility of covalent substances can be significantly influenced by whether they react with water or not. So with ammonia, we have NH3 in water, so aqueous solution, plus more water, and we form an cation, so ammonium, and then the hydroxide ion. So in carbon dioxide, it's the gas, which we bubble through water, the liquid, and we can form H2CO3, which is going to be an aqueous solution because we're dissolving it in there. So both the dissociation and ionization procedure in ions in solution are these two. So the difference in dissociation of ionic compounds is that in ionic compounds, the ions are already present. So in the lattice structure, they already are in ion form, and in this, and they're able to move about in the solution to dissociate. In ionization of covalent molecular substances such as HCl, the ions are formed in the reaction with the water. So this one, in ionic compounds, the water is not involved in forming the ions, but they are in the ionization procedure for HCl. So insoluble large molecules are large covalent molecules that don't dissolve in water and most other solvents. And these include cellulose and polyethylene. So they have very strong covalent bonds in the molecules, and that's why they're so large. Bonds cannot be broken because remember, covalent bonds are one of the strongest bonds, and weak intermolecular forces such as hydrogen bonds and dispersion forces can't overcome this. So what we get is that we have covalent bonds within the large molecule, and they hold it together, so we can't ionize it or do anything to the structure of it. So cellulose and structural proteins like hair, silk and wool are all discrete molecules. That means they form specific molecules. They're not bound to anything else or interact with anything else. And they're large and held together in an orderly manner by hydrogen bonding, like DNA. Therefore, water cannot separate them into individual molecules, and therefore it's insoluble in water, because the water can't attack the intermolecular bonds because they're so big and those spaces cannot be penetrated by water. So some of the macromolecules that are soluble include starch, which is a sugar, glycogen, which is another sugar, and some proteins. They form a complex 3D structure and cannot be packed together neatly into crystals. So that means if it's not in a crystal form, there's a lot of space in between. So water can get in those spaces and separate them into individual molecules. But covalent network solids, so silicon dioxide, and diamond, which is a carbon one, have covalent bonds in between the network to make the 3D structure. And remember, covalent bonds are the strongest ones, so we can't really break them. And therefore, they must be insoluble in water and most other solvents. So the covalent bonds are strong, and they form the crystal lattice, so it can't be broken very easily. And therefore, weak intermolecular forces like hydrogen bonding and dispersion forces can't break them, so they can't be dissolved in water. When some ionic compounds crystallize, so that means we're taking the water out and it's reforming the crystal structure, from an aqueous solution, we can produce pure crystals, so that means there's no water in them. But water can be attached to some of these compounds. So when we crystallize it, so we're trying to get rid of all the water and evaporate it, sometimes water gets trapped in there, and that's the water of crystallization. So some salts contain water in their crystal structure normally, and this is what we call a hydrate. But some of them that don't contain any water and purely are just the salt, we can call them an anhydrous lattice or crystal structure. So the an here, the an, means doesn't have any hydrous bits, so no water. And some of these examples with the hydrates are the copper sulfate, which has, for every 1 copper sulfate molecule, you're going to have 5 water molecules bound around it. And similarly here with 10 and 7. And here, this calcium sulfate will only have 2. And 8 for the barium hydroxide. So in this lesson, we were just looking at getting molecules and how they dissolve in water. So for a big molecule, they can be dissolved in water if they allow water to attack it and penetrate the structure. And sometimes when this happens, we'll get some either full solubility, partial solubility, or not soluble at all when they can't. But when we take out the water again, we can reform crystal structures in ionic compounds, and sometimes we can have pure crystal structures with no water, but some of them are going to have some water still attached to it, like these compounds, and therefore when we form the salts, they're called hydrates because there's water involved. So now we can answer a few questions. So question 11, draw a diagram to show the hydrogen bonding interaction between methanol and water. So here we have water coming in, forming hydrogen bonding with the methanol. So we see here oxygen being electronegative, negative charge here, positive charge here, can form hydrogen bonding with the water. So oxygen with the hydrogen because opposite charge, and again here oxygen and hydrogen opposite charge, and on this side water doing the same here, and then the methanol coming in on the other side of the water. Next, question 12. Explain the difference between ionization and dissociation to form ions in aqueous solution. So ionization occurs when a previously non-ionic substance produces ions once it reacts with water. So we have something that's not ionic, so a proper, like just a normal molecule, and then when we put it in water, there's a chemical reaction, and this forms ions. So it's ionization. Dissociation, however, we already have ions present in the crystal structure, and the dissociation is a separation of these ions to form to go into solution. So they have ions present before and after. So next, question 13. Calculate the mass of 1.3 moles of hydrated calcium sulfate in grams. So calcium sulfate is here, CaSO4, and with every CaSO4 molecule, we're going to have 2 sets of water molecules bound, not bound to it, but attached with intermolecular forces. So we have 1.3 moles, and we're going to add up altogether the whole mass of this compound. So calcium sulfate, there's 4 oxygens, denoted by O4 here, and 2 sets of water. So when we do this, we have 6 sets of oxygen because 2 come from the water, 4 come from the SO4, and 4 sets of hydrogen because 2 times 2 is 4. We can then see that these are all the molar weights. So we just put them all in. So calcium is 40.08. The sulfur, we put that in. Oxygen, 6 times of it though, remember, because there were 6 oxygens and 4 hydrogens. So when we do all the math, we end up with 223.8 grams. So question 14. Although oxygen is not that soluble in water, but when it is bubbled through water, it partially dissolves in the water. Explain how oxygen can be slightly dissolved in water. So oxygen, remember, is a diatomic molecule. That means 2 oxygen atoms bound together covalently. And when we bubble it through water, the oxygen molecules form weak dispersion forces with water molecules. Because remember, water molecules, even though they have majority of hydrogen bonding, they still can have some dispersion forces. So the attraction is not very strong because it's mainly hydrogen bonding in water, but whatever is left is the dispersion forces, and this can interact with oxygen, and therefore oxygen can be dissolved in it, but it's not very soluble because there's not much dispersion forces to interact with. So question 15, true or false? Cane sugar, methanol, and ethanol are all water soluble because they are small molecules. The size of the molecule does not always depict solubility. Sometimes large molecules can dissolve in water very easily. To be soluble, the intermolecular forces will form between the water and the compound that we're looking at. So in this case, methanol molecules. So in this case, they must be stronger. The water and the methanol interactions must be stronger than the methanol-methanol ones. So we need to overcome the methanol-methanol ones to break it up and make it soluble. So in this case, methanol, it's false because not all of them are involved. Sometimes we have strong intermolecular forces, and therefore they can be disrupted with water. But if they're too strong, some small molecules can have very, very strong interactions between themselves, and water can't overcome this, and therefore some of them, that means it's insoluble, and some small molecules are insoluble in water. So just to recap, what we looked at was covalent molecules and how they dissolve in water. They usually need to be polar or have a polar end, and they need to be quite small. If they're too large, then they can't always interact very well with water. Sometimes we have dispersion forces such as oxygen and oxygen interacting with water with some dispersion forces as well, and therefore we can get partial solubility compared to full solubility.